In this demonstration video, I will explain how to design a constant current charging and a constant voltage charging method for a controller using MATLAB and Simulink. Batteries are more frequently damaged by inappropriate charging than by any other cause. For lithium-ion batteries, a two-stage charging method is used. During the first charging stage, the constant current stage, the charger produces a constant current that increases the battery voltage. Generally, a higher potential is used or a boost converter is used for increasing the potential, charging potential of a battery pack. Hence, there is always a problem of overcharging. This is the reason, and some other reasons are also there, like Coulombic friction, increase in charging temperature to prevent thermal runaway. This constant current charging and constant voltage charging method is applied in charging controllers. The first stage is the constant current charging stage, and the second stage is the constant voltage charging stage. In the first stage, the charging current is kept constant while the potential slowly increases to the required battery potential. After this stage ends, then we enter a constant voltage charging stage where the battery potential is maintained without any further increase in charging potential. And during that phase, slowly the current is reduced, and it is reduced exponentially. So let's design this constant current charging and constant voltage charging method for a charger controller using MATLAB and Simulink. So I have opened a Simulink workspace. In this Simulink workspace, we will add our blocks in order to design a constant current and constant voltage charging schematics for our controller. These schematics can be converted to a code and can be uploaded to the required hardwares for their functionality. So the blocks that we require in order to model this are follows. So first we need a battery. I'll go to the library browser and I will search for a battery. Here we have a battery. Let me just drag and drop the battery from the library. I'll double click on the battery and I will edit the battery properties. For this lesson, we are going to use a 48 volt and a 94 Ah battery. The initial state of charge will be 88. Apply and close the parameter edit block. So now we will be adding a voltage source, a DC voltage source. So DC voltage, we'll add a DC voltage source. Let me edit the properties of the DC voltage source. We will use a 32 volt DC voltage source. Why do we require 32 volt? Because we will be using a boost converter in order to boost the power output or in order to boost the voltage of this DC voltage source. So in order to create a boost converter, I require a subsystem. So I'll create a new subsystem. I'll open the subsystem. So in order to create a DC to DC converter, not a DC to DC, but a boost converter, boost power converter. Generally, we require inductor and a capacitor. I'll just keep the inputs and outputs. I'll be requiring them later on. For creating an inductor, I will call my series RLC branch. From this, I will only use the inductor. I will use an inductance value of 10 microhenry, 10 E minus 6. This inductor will be coupled with a capacitor and a diode to prevent backflow and voltage short, or voltage, you can say, short falling or voltage falling. I will call a diode block from my power electronics block set. I'll connect this diode block to my inductor. I also need a gate. or a IGBT to efficiently switch my loads or efficiently switch my circuit. Switching means it will switch on and switch off the boost converter depending on the power requirement. So this is IGBT. IGBT means internal gate bipolar transistor, that is generally used for switching high power circuits where higher potential and high current is used. MOSFETs are used in low power circuits. In your small electronic devices, MOSFETs are used. In your not large heavy electronic devices where more potential and current is used, we use IGBT for switching. I'll just copy and paste this inductor, because from this inductor block I will use, or I will get my capacitor block. Let me connect the capacitor to the diode. I will use a capacitance of 100 microfarad. I'll be using a capacitance of 100 microfarad. Then let me just use my in and out blocks. So in here I have in and out blocks. I'll not be using this in and out blocks. Rather, I'll be using my physical connection ports. That will be better because I can represent things more vividly if I use a physical connection port or a PMC port. I'll name this port as in positive. I'll just copy and paste this port, and I'll name it as in negative. Let me just connect these ports to my other components of the circuit. Then this circuit will have an output. So again, I'll just copy and paste this connection ports, Ctrl R to rotate it. Then I will connect. Instead of in, I'll write out positive. Let me copy and paste it, and out negative. My boost converter is completed. Now all the ports are on the same side. In order to change the side of the port, what you have to do is double click, and port location is left, change it to right. Now my ports are at their required locations. I also need one signal port. In this, I also need a signal port for switching off and switching on my IGBT. So for that I will use a in port. There are various kinds of ports used for modeling. The physical connection ports and the in ports. In here I will provide my name S plus signal port. My subsystem is done. I will rename the subsystem to boost power converter. Now I will use a cutoff IGBT in order to connect my VDC to my boost power converter. The VDC negative port will be connected to the in port and the positive will be connected to the positive input. Let me arrange it properly. Now in here I will also use a IGBT in order to create a source cutoff. So I will use a source cutoff IGBT in order to control my DC voltage cutoff from my boost power converter. So for that I will call another IGBT and let me connect that in here. For that I have to delete this connection and again I have to connect the IGBT. Now my boost converter is completed. But not only we need a boost converter, we also need a EMI filter or a electromagnetic interference filter. So I'll be creating a new subsystem. Why do we need a electromagnetic interference filter? Because your IGBTs and other electronic devices may interfere, may produce magnetic waves, or they may produce electromagnetic waves that may interfere with the working. So I have to clear those noise generated by those waves by using a EMI filter. For that I will create a new subsystem. Again I will use my physical port for connections. So for an EMI filter we just need a inductor, a high value inductor and a capacitor. So let me call a series RLC branch. From here I will call an inductor, I will copy and paste it and I will call a capacitor. Let me rotate the capacitor. This much is required for a EMI filter. Now I need connection ports. This connection port is my IN positive. And I'll be copying and I'll be pasting another connection port that I will name IM negative. Let me connect the connection ports. Now I need outputs. So I'll provide a output with the same connection port. These are inputs and these are outputs. Sorry. This is my out positive. Then I also need a ground connection. So let me copy and paste it and I will name it as my ground. Same negative can also be referred to as a ground. Namings are important so that during connection or during debugging, it won't be difficult to recognize the systems or the components. This is the reason why namings are important. I'll edit the value of my inductor. I'll provide a value of 0.005 Henry and a capacitance of 1000 microfarad. So my EMI filter is done. So I'll name this one as also ground. Why? Because my subsystems or this subsystem needs a ground. A EMI filter needs a ground. Now I'll just change the location of my connection ports to right. This is the advantage of using a connection port. You can specify the location, or else output and inputs can be used, but location specification is not allowed. Let me connect my out to N and out to ground. Now I'll rename the subsystem to my EMI filter. So my EMI filter is done. My source cutoff is also done. Source cutoff IGBT. So source cutoff means this is used to cut the source, this voltage source. And I also require a load cutoff IGBT. I'll just copy and paste it for reuse. Let me flip this block. So I'll go to the format, flip block, I'll flip it left right for proper connection. Now this is my load cutoff IGBT. My source cutoff IGBT and my load cutoff IGBT. Let me give some collars to these subsystems so that during any debugging operation I can easily recognize which one is my boost converter and which one is my filter. Press spacebar in order to fit the model to your screen. Now, my boost converters and EMI filters are done, but still my controller is yet not ready. In order to create my constant current charging and constant voltage charging, remember, till now I have not applied the constant current and constant current charging methods, constant voltage and constant current charging methods. I've just created some of the basic, that is a boost converter and a EMI filter. These are the basics of building blocks of any charging. You need a boost converter to boost the input and a EMI filter to remove any electromagnetic interference. Now I will create a new subsystem where I will have my constant voltage and constant current charging schemes. Controller. Now in this controller, I will have my constant current and constant voltage charging schemes. So first I will create inside this I will create another subsystem and I will name it as V charge. V charge means this will provide me with my constant voltage charging methods or constant voltage charging. So in order to create a constant voltage charging, we need a V reference. What is the reference voltage? The reference voltage will be equal to the full voltage or the terminal voltage. The reference voltage will be equal to the terminal voltage. Okay. Now we will be using a PID controller in order to control our voltage output. So for that, I will use, first let's see, I will use my inputs. These are my inputs, so I will just change their orientations. I will name it as V bat. That means voltage from battery, the voltage reading from the battery. I also need another input, that is my V ref, that is my reference voltage or my full charge voltage. Okay, I require these two as my inputs. So I'll just rotate them. And I will be requiring an output. The output will be my duty cycle. Remember, this demonstration video is a video from a full course of hybrid electric vehicle design, MATLAB modeling in MATLAB, and product design using MATLAB. Hence, these duty cycles are already discussed in previous chapters. So for generating a duty cycle, we need a V bat, then we need a gain. To convert the V bat to normalize the V bat. Normalize means I'll divide this with 58.4. What is 58.4? This is the maximum potential of the battery when fully charged. This is the maximum potential of the battery when fully charged. Then I'll go for a sum block. The sum block is used to find out the error between the maximum voltage and the reference voltage. If the maximum voltage is equal to the reference voltage, then the error is 0. That means we have achieved a constant voltage charging. If the maximum voltage is not equal to the reference voltage, then we have not achieved a constant voltage charging. So the PID requires tuning the signals. I'll go with my PID controller. PID controller is a proportional integral derivative controller. This controller is also discussed in previous sessions. It is used for controlling the past, present and future values of your signal. PID means proportional, integral and derivative. Proportional controller is used to act on the present value. Integral controller is used to act on the past values. Derivative controller is used to predict the future values. Proportional to act on the present value, integral to act on the previous values or past values, and derivative to predict the future values. So the values that I will be providing in here is 0.65 for my proportional coefficient and 150 for my integral coefficient, and derivative coefficient will be 2.7 E6. I have got these values through calculations. You can also get these values if you go for tuning, manually tuning the PID controller. I'll go to saturation. I'll limit the output. The duty cycle limit is from 0 to 1. So I'll limit it from 0 to 0.9. I'll go with OK. So my V charge is done. I'll just rotate this one. Then I need my I charge. So I'll just copy and paste this block. I also require the same systems for my I charge or for my constant current charging. So V charge is there, I'll just name it as I charge. That will send the charging signal for current. Now instead of V bat, I will use I bat. The maximum charging current that we will supply to the battery is 100. So I'll divide this current with 100. This is the maximum current that we are going to send to our battery. Same, when Iref is equal to the battery current, then we have achieved a constant current charging. If not achieved, then the PID controller will tune the signal to achieve a constant current charging. I'll again provide the values to the PID 0.75, then 50 and 3.2 e to the power -6. I'll go to saturation and I'll limit the output 0.9. Since I have copied it, so these values are there. So this is my constant current charging scheme or method. Now the most important thing, that is my algorithm to control this constant current and constant voltage charging. I will not show you in this demonstration. The development of the algorithm is not covered. In this demonstration, the development of the algorithm is not covered. So I'll just use a previously modeled algorithm. So this algorithm will provide me my Vref and Iref values. I'll just connect them to my Vref and Iref values. Then SD value is the signal that will be provided as a output. This signal is used to switch on our IGBTs. Now I also need a digital clock to mark the time or to keep account of the time. This V and I will be the input from my batteries. So I'll go for my input again. I'll just copy and paste it. This is my I bat, means current from the battery. This is my V bat, voltage from the battery. Now these two duty inputs or duty outputs will be provided to a multiport switch. This multiport switch is used to efficiently switch between the constant current and constant voltage charging requirements or demands. Then this signal for when to start the constant voltage charging and when to start the constant current charging is provided to this multiport switch for efficient switching between these two modes. Then I'll call a constant to block the output from my port 3. I'll go for 0. that is the off signal. That means if none of them is providing any signal, or if there is no signal from my charger, then this zero signal will be provided, that is off signal, that is charger is switched off. I'll delete this one and I'll use another output. This output will be my net duty. Now my controller is done. I'll get the okay. So one thing, I have to rotate it. Controller is done. The VBAT, from where I'll be getting the VBAT and IBAT. For that, I need to connect my current measurement and voltage measurement devices. So this current measurement device, I'll be connecting it between my battery and the IGBT. This will measure the current. Then for voltage, measurement, this will again I'll connect it. This voltage I will connect it between the positive and negative ports. I'll just drag this current port to my IBAT and just drag this voltage port to my VBAT. Now this duty, this SD, remember this SD will be provided to my IGBT for source cutoff. This SD will be provided to my IGBT for source cutoff, and this SD will also be connected to this load cutoff, depending on the, that means source and load will be cut off simultaneously or depending on the requirement. Now this duty cycle will be provided to a PWM generator, a DC to DC PWM generator. The duty cycle is the input. We will have a switching frequency of 20,000 Hz. Because your IGBTs are actually high frequency switch. Your IGBTs are actually high frequency switch. So the switching frequency will be decided, or it will be generated by this PWM generator by the input from controller. Now let me call a scope. All the modeling is done. Now we just have to analyze our problem, or you have to run it. So I'll call a bus selector. This bus selector is used to select the signals from my components. So I want the SOC output of my battery and I want to plot it. I also require some more outputs to visualize. So I'll go for 3 outputs, and how to plot them also I will select. I have selected how to plot. Then after I will my current output and my voltage output. IBAT and my VBAT. Now the modeling is done. All the things are Done. Now let us analyze this model. I'll close this one. Let me refit the model. Let's see the constant voltage and constant current charging schemes. So I've kept it as 88. I will keep it as 89 so that we can reach the constant current and constant voltage charging as fast as we can. Remember, this constant voltage and constant current charging scheme is not dependent on the SOC. Most of the constant voltage and constant current charging methods, or some of the constant voltage and constant current charging methods depends on SOC. That means the constant voltage will be maintained until 80% SOC. Constant current will be maintained, until 80% SOC. After that, constant voltage charging will start. But the SOC may fluctuate. It may vary depending on the age of the battery. So this constant voltage and constant current charging method that we have designed in here is not dependent on SOC. Rather, it is dependent on the terminal voltage or the max voltage. When we reach a required voltage, our constant current charging will stop and our constant voltage charging will start. So this is much more robust. Why? Because it removes the effect of changing SOC because of life, change in value of SOC because of life or degradation of the battery. Now let us plot our results. So I'll just save it first. Let me run it and let me see whether it is running properly or not, and let me save it. So there are some errors. It is asking that you require a power GUI. So whenever we perform any electronic calculations or when we design a circuits and use electronic circuits or electronic components like capacitors and inductors as well as IGBTs, we need to set up our solver in a specific way. That means the solver configurations should be set to solve a problem like this. By default, MATLAB solutions or MATLAB solver is set to solve certain types of signals by default. So we have to change that default to a setting where we can solve our problems involving gates and electronic components. So I'll provide a sample time of 1e minus 1. And it will be discrete. Why discrete? Because gates are there. Switching on and switching off will happen. So our signal is no longer continuous. When switching off and switching on happens in your electronic circuit, then the circuit signals are no more continuous. They become discrete. So let me just run the model from my scope. So we can see a constant current. You can see how the current is constant and the voltage is increasing. So this constant current, actually you can see there is a little bit up down. Actually just see the difference. It is fluctuating from 99 to 100 amperes. So the fluctuation is just 1 ampere. Okay. So we can keep it as constant. The fluctuation is very less. Okay. Since we are using different scale, so this fluctuation is visible more. But if we use a small or a very big scale that is from 0 to 100, the fluctuation will become, or it will be negligible. And you can see how our potential is increasing until we reach, you can say, our required battery potential. So after we reach the required battery potential, then our constant voltage charging scheme will start. Okay, you can see now when we are using 0 to 100 scale, the current is constant and the voltage is increasing, but the axis is actually rescaling itself to plot properly. Okay, these fluctuations will be there because we are using filters and we are using electronic components. So this small amount of fluctuations will be there. But as the axis will rescale itself, we can get the proper readings. So my voltage will increase up to 58.4. Then we will enter our constant voltage charging. Then we will reach, then after 58.4 we will reach our constant voltage charging method. So let it run. So it will take some time. So I'll be ending this demonstration video in here. The full video can be accessed in the website. You can follow that. So thank you.